Okay, so yesterday we started on 5.3. Today we continue that. This is where we got to yesterday. I'll collect homework at the end of class. Okay? Just so I want to get things rolling here. So, remind me. The functions that we talked about yesterday were sine, cosine, and tan. And we were just saying that the domain is all real numbers. So I just want to remind you what that means. Most of you understand a domain pretty well. But I think there's a few people out there still who don't really understand what it means to say domain. So what it means is this: when you are turning on your calculator, whatever you're allowed to type for that function, that's your domain. So, for example, sine 20, let's make sure this is in degree mode for this lesson. Sine 20 is an awkward number, but it does exist. Okay? So 20 is definitely in the domain. Okay? Sine 30, that's not an awkward number. It's actually right on the unit circle. It's the y-coordinate 0.5. Okay? But the truth is, you can type sine of anything. The calculator will never say error. It will never get grumpy. Okay? It'll always give you a response. So we'll see that. Okay, so you might say, well, that's not really proof. Maybe I could spend a couple hours typing random numbers, and maybe one of these times the calculator will say error. No, that's not going to happen because, look, sine means the y-coordinate, right, on the unit circle. So you tell me which of these green points does not have a y-coordinate. They all have a y-coordinate. If you have a point on the unit circle, I don't care where it is, there's a y-coordinate for it, right? That's equivalent to saying that every angle has a sine value. Okay, so sine's not very interesting. The domain is all real numbers. The same thing happens with cosine. Okay, you can look at this picture again. Cosine is going to accept any real number because for every one of these points, that's another way of saying for every angle, there's always an x-coordinate. All those points have x-coordinates, so they all have a cosine. All right, let's go to tangent. So tangent, we were talking about that. We were saying tangent's a little different because with tangent, there are certain things you can't type. Does anyone remember what they are? You can type tan 0. Tan 0 is well defined. It is actually 0. You cannot type tan 90. Remember that? Why? What's so bad about tan 90? It says error domain. Yeah, the problem with it is tangent means y over x, right? So what's going on at, let's move this down here now. What's going on at the top of the circle is at 90 degrees, the x happens to be 0. This is the point 0, 1, and we have trouble with dividing. So although there is a cosine there, 0, and there is a sine there, 1, there's no y over x. So we run into some problems with 90 degrees. And this happens at the bottom of the circle too, doesn't it? 270 has the same problem. We cannot do y over x there. But those are not just called 90 and 270. 90 is also known as 450, right? Same location. 630 is the same thing as 720, 270 I mean. It's the same location. So there are many names for those 2 points. And basically any odd multiple of 90 is forbidden. So for example, 1 times 90, 5 times 90, 10 times 90, 1 times 90, 5 times 90, 9 times 90, okay? Or negative 99 times 90. Any odd number times 90 is forbidden. All right? So I'm just going to try something real quick. It's kind of silly. But I'm going to type, if it won't accept tan 90, maybe it'll accept tan of negative 321 times 90. You think it'll accept that? No, it won't take it. Why? Because 321, negative 321 is an odd number. And odd multiples of 90 are forbidden. See? So we're seeing that here. We can't take it. Okay, let's go to cosecant. That's the next function we would talk about because that's the reciprocal of sine up top there. So cosecant is reciprocal for sine, right? Okay, so what is the domain? Well, you don't really have buttons for these. or at least they're kind of hard to find. So you just have to reason with me here. If cosecant means 1 over y on the unit circle, or r over y if you're not on the unit circle, either way, what is being forbidden here? What cannot be 0? Look at the fraction. Y cannot be 0, right? So where would that happen? Is that even possible? Yes, it happens here and here. At the point 1, 0 and the point negative 1, 0, we have a problem. We cannot find cosecant because we can't find 1 over 0. Okay, so we have problems with a different set of angles this time. What are my forbidden angles this time? 0 is forbidden, right? That's the point on the right. 180 is forbidden. That's the point on the left. So theta cannot be 0. Theta cannot be 180. 0 is also known as 360, right? 720 would be forbidden. 540 would be forbidden. Basically, any multiple of 180 is not allowed. So we can summarize this by saying theta is not a multiple of 180. Or you could just write k pi. So I want to remind you that this isn't supposed to be intimidating. 2k plus 1 times pi over 2 just means an odd multiple of 90. That's all this means. And this just means a multiple of 180. Those are forbidden. Okay, the other two are easy. We've already done everything we need to do. Secant is defined as 1 over x on the unit circle, so it should have the same domain issues that tangent does. Right? Tangent is y over x, secant is 1 over x. They should have the same domain concerns. So theta cannot be an odd multiple of 90 degrees. Right? And cotangent, that's defined as x over y. That's going to have the same domain issues as cosecant, which is 1 over y. So theta cannot be k pi. So I'll just restate that real quick for those who are listening. The secant function has the same domain issues as the tangent function because it is 1 over x, and tangent was y over x, right? And cotangent, the last one there, is x over y, so it should have the same domain concerns as 1 over y. Either way, y can't be 0, and theta cannot be a multiple of pi. Yes, this is supposed to be a not equals to. So sometimes we declare what theta can be by saying what theta can't be, right? That's kind of how we do domain. Some of you mixed that up on the test, by the way. I asked you what values of x are in the domain, and you told me all the things x couldn't be. Okay? But you didn't do like not equals. You actually wrote equals. X equals 3. You know, x equals 83. No, those are forbidden values, see? So be careful with that. Some of you put x is less than 3 is allowed. You meant x is greater than 3 is allowed. You were giving me the restriction, but you didn't state that it was a restriction. So I had to take off some points there. All right. Okay, I hope this table isn't mystifying. It's very simple. It means that when you use these buttons on your calculator, there are certain things that you're allowed to type in as an input. Okay? You have no business typing tan 90. Okay? That doesn't even make sense to the calculator, and it shouldn't. Okay, but let's suppose you did give the calculator values that made sense. What sorts of answers would it be giving to you? This is almost a more important question. This is the question of range, and we've avoided it like the plague this year because the best we can do right now with range is I can give you a picture, and you can look at the y values and tell me kind of where they fall. But have I ever given you a function and asked you for the range? Not really. Maybe some of these simple flashcard functions. Okay? So that's our next discussion. What is the range of these guys? I'm going to switch to blue. So let's do sine theta. What is the range? There's so many ways to learn this and understand this. But one is to understand that on the unit circle, sine is y. Isn't that true? Okay. So if I draw a unit circle, and on the unit circle I draw all these blue points, we've already talked about sine's domain. That means we put a dot any which where we want, anywhere, and there's always a sine value, there's always a y coordinate. But I would like to know what those y coordinates are quantitatively. Like, what kind kinds of y values fall within this unit circle. Remember, the top of the circle is at 1, and the bottom of the circle is at -1. So you tell me, what kinds of y coordinates do these blue points have?
Y is less than 1 and greater than 1, greater than.
Yeah, you can see that every one of the blue points is going to have a y value at most 1 and at least -1. Okay, so you can write that like this, or we can use our interval notation and write it like this, which is how our book does it. So just for kicks, let's take out our calculator and be creative. Let's just type, sine of whatever you want. If you get something bigger than 1, something is wrong, okay? So I'm just going to mess around with this. Let's try it here. Let's do sine 25. That's kind of fun. And then let's do sine of 25,000. Obviously, they're not the same answer, but they are both less than 1, right? How about sine 24,050? Or let's do 24,950. I don't know, I'm just messing around. Ooh, that's getting closer to 1, see? How about sine of 24,900? 0.866. See what I mean? There's no numbers bigger than 1. And you can certainly get negative answers. We've had that already happen. So the answers are between -1 and 1. Okay, let's talk about cosine. Cosine is the x-coordinate of all those blue dots. But isn't it true that your cosine is also going to be between -1 and 1, because all of these points have an x-coordinate greater than or equal to -1, yet less than or equal to +1. So we can write the same exact thing for range here on cosine. Okay? Let's talk about tangent. Tangent's a little more interesting. It always is. So what happens with tangent? Well, we've already talked about certain angles we're not allowed to punch in. Remember the first one, 90? You cannot type tan 90 and make any sense of it. So I'm curious, what happens at 90? Like, why is it forbidden? Well, we said you can't divide by 0. Yeah, that's true. I wonder what would happen if we just kind of ran through a little exercise here. And let me erase my answers so you don't see them. I want to do tan. I want you to see them. Tan 80, tan 85, tan 88, tan 89, tan 89.9, tan 89.99. Let's just play around with our calculators for a minute. What are you getting? Are you all in degree mode? I'll go in degree mode. Degree. Should be in degrees mode. Start punching them in. Just kind of curious what's going on here. I said degree. Can't talk. All right. Tan 80. What's that? Okay, 5.67, yada yada. Okay, what's tan 85?
11.4.
All right, fine. What about tan 88? Okay, so I can't hear you exactly. You said 28.6 something. Listen, we already see that this is not the same rule that we had for sine and cosine. Sine and cosine was giving us strictly by between -1 and 1. We've already broken that. Okay? So some other rule for range here, isn't there? All right. Let's talk about tan 89. What's tan 89? 57.28. Okay. We'll say 57.3 then, if it's 57.28. What's 89.9's tangent? It's roughly 573-ish, right?
89.99 is 5,000.
So close to 5,730. So what's going on? It seems like the closer we get to 90, the larger this value is, right? So let's try and make sense of that from the unit circle's perspective. Please pay attention. Okay, so let's imagine you're on the unit circle, and you decide to get really close to 90 by going way, way up here, right? So you pick the point 0.9 comma, I don't know, 0.01 or something. I don't know what it is. Those are reversed, sorry. I need my x-coordinate to be small and my y-coordinate to be close to 1. Okay, so this is like 0.1-ish, and that's like 0.9-ish, right? The ratio between these two is already 9, right? 0.9 over 0.1 is 9, okay? If you go closer, let's say you bring that point even closer to 90, the x-coordinate is going to decrease. Let's make it 0.01 now. And the y-coordinate is going to increase a little bit. You're getting closer to 1 for the y. What's the ratio now? 999. See what I'm saying? So while the x is shrinking, the y is growing. So you're dividing a big number by a tiny number, and it gets huge. Big over tiny is massive. Okay? Big over tiny is massive. All right? And this could go all the way to infinity, right? If that were such a destination. So let's go back now and answer what we think the range is. We think that the upper limit is unbounded. It seems like it just basically goes all the way to infinity. We can't put a closed bracket on that, right? Some of you put a closed bracket on infinity. You can't do that. Can you have negatives? Well, sure. Imagine doing the same exercise, only using 10, negative 80, 10, negative 85, and so forth. You would have gotten the same results, only negative, actually. So negative infinity is our quote-unquote lower bound. So what do we have? All real numbers. All real numbers is our range. Did I prove it? No. Does it make sense? Yes. You can get anything from dividing numbers between negative 1 by numbers between negative 1 and 1 divided by number between negative 1 and 1. You can produce anything, even a million. Okay? Let's talk about the other three. So the next one would be cosecant theta, also known as 1 over y on the unit circle. Listen, if y is a number between negative 1 and 1, and we divide 1 over that, so what happens if you divide 1 over 0.1, or 1 over negative 0.1, or 1 over negative 0.99? What's going to happen? The top will always be larger in absolute value than the bottom, right? Thereby giving you a number greater than 1. Or if it's a positive divided by negative, it'll be a number less than negative 1. This is easier for some people to understand than others. But let me just say it this way. If the the range of sine is a number between negative 1 and 1, then the range of cosecant will be the exact opposite of that, and it will be all numbers not between negative 1 and 1. Maybe you understand it that way. Okay, so the range on this is a little different. It's basically all numbers greater than or equal to 1 or less than or equal to negative 1. We can write that mathematically as anything from negative infinity all the way up to negative 1 inclusive, and anything from 1 to infinity. So this one we probably would want to play around with our calculator again. Maybe we can type like 1 over sine 20, 1 over sine 90, 1 over sine 100. Let's just goof around with the calculator. Let's see if it's true. All right, so we have 1 over sine 20. 2.92, like we said, it's not between negative 1 and 1. How about this? 1 over sine 90. Exactly 1. Okay, that's okay. We can add 1. We just said can't have something between negative 1 and 1. All right, how about this? 1 over sine 91. Yep, slightly greater than 1. How about 1 over sine 89? 0.99? Oh, I typed it wrong. I meant to type 1 over sine 89. There we go. 1.001. So you cannot get a number between -1 and 1. You're not going to get a number between -1 and 1. Exclusive. Actually, secant works the same way. It's 1 over x, so it has the exact opposite range that cosine did. But that's the same thing that happened with cosecant and sine. So same exact answer for this one. And the last one is cotangent. And if y over x can produce any real number, then x over y can produce any real number. So this is all real numbers. Now all of this is in your book. Okay? I could have just referred you to page whatever. Okay? Everybody look at page 401. It's right there. The whole thing. Both tables. All summarized into one nice table. But I don't see the value in that. I think you need to think about these things yourself. Maybe you can goof around on a calculator until you really learned them. You have to have this memorized and the previous table memorized, domain and range, for the test. Some people would prefer to just reason it through, like we did just now. Kind of reinvent the wheel on the day of the test. I can probably tell you who's going to do that. Just remember, there's a lot of things to do during the test, so you don't want to spend too long reasoning. The more facts you have memorized, the faster your test is going to go. But you're welcome to just rethink this. What's 1 over a number between -1 and 1? Y is greater than 1, y is less than -1. You know, you can do that if you want, or just memorize it all.
Are we going to be able to use our calculator on the test?
No. There's a portion of the test where you need it, okay? But most of the tests you'll not be allowed to use a calculator. Okay? All right, so domain is important, range is important. Okay, now what we're going to do is continue goofing around with our calculator. Okay? Some of you have a little more background than others with sine and cosine, that sort of thing, so please do not shout out the answers if you know what they are. It ruins the activity for everyone, okay? So here's what I'd like you to do. I'd like you to fill in the blank with any number that works, okay? So make sure your calculator's in degree mode. Fill in the blank with any number that works. Any number that makes the statement true. Don't give me the answer. Write on your paper. Some of you know this. You know exactly what to do. Others are like, wow, this is new. I've never seen that. I need everyone learning. So don't shout the answer. Grab your calculator. Test your hypothesis. You think you know the answer. Test it. Double check. And as we find new facts, we'll record them. And then we'll find them in the book anyway. Okay? Trying to figure out another angle that would give you the same sine value as sine 47. Okay, well sine 47 is 0.73135. Okay. Does anyone have another angle that gives us the same value? So what did you put, Jack? Sine
Well, I just put it in my calculator as an algebraic function, and it comes out with Ln plus 0.36.
Okay. Yep. Jack, you had your TI-89 solve the equation sine x equals sine 47?
Yeah.
Okay. Yes?
I did sine 407.
407. Okay, let's try it. He says 407. That's definitely going to work. It's the same answer. So, can you justify it?
I guess.
How would you justify that? Like, why is it going to work?
Because 407 is 360. Like, if 47 plus 360 is 407.
Okay.
And so that's the same area as 47 degrees would be. Like, if you went around that unit group, like, it would be at the same point.
Yeah.
407 and 47.
So the proper term there is coterminal. You would just say that 47 and 407 are coterminal. It means they're in the exact same spot, same stopping point when you're rotating. So if they're the same spot, they have the same y value, and therefore the same sine value. Okay, there's more. There are many, many answers to this question. There's an infinite number of answers. What's another answer Daniel, you had your hand up too.
133.
133, that's an interesting one. Did anyone else have that one? 133. Okay, let's talk about that. First, let's verify it, right? So let's see if it's really true. Sine of 133. Let's see, sine 133. 0.73135, same exact number. What is going on there? This is a little bit less obvious, than the 407. So what's going on there? You want to explain it?
I just thought it was the same distance away from 90, so and plus it has the same y value, so it's the same.
Yeah, I'm going to explain it the latter way, the second way you said it, just because that makes more sense to most people. If this is the unit circle, and 47 degrees is plotted, it's right about here, right? We know that it has a certain x coordinate and a certain y coordinate and a certain r, in this case 1, right? But there's another point that has the same sign because it has the same y and r, right? Namely this one right here. This point right here is directly across the y-axis from the first point I drew. Both points A and B have the same y value. So they have the same sign, right? Okay, so this should have the same sign value as point A. And if this is 47 degrees, and this is 47 degrees, we can figure out what angle point B is actually at. It's at 180 minus 47. Okay, so we learned something new. Okay, we actually just learned two things just from goofing around. We're going to write them down right now. One of them is in this section, one of them is in a future section, but we learned both, so let's write them both down. We learned that sine of theta is always the same as sine of theta plus as many 360s as you wish. For example, theta plus 360, that's coterminal with theta, so the sine value doesn't change. If you add 720 to the angle, you're back at the same location, the sine value doesn't change. The less obvious one, which I don't even think is in this section, we also discovered, thanks to Daniel, that a sine of an angle is the same as the sine of its own supplement. This is the one I want to test out a little more, Like, let's go ahead and try a couple more examples of this. Is it really true that sine of 10 degrees is the same as sine of 170 degrees? Those are supplements. Let's see. Yep, sure enough. Sine of 10, sine of 170, same result. How about sine of 179 and sine of 1? Those are supplements. Sine 179, sine of 1. Same answer. So we learned something brand new there. This is a very, very important identity. Okay? Very important identity. It's called an identity. So there's two rules right there. I have another question. What would happen if we did, let's say, sine of 20 and sine of negative 20? Like, what's the difference? You know what I mean? Like f of x and f of negative x. Maybe we can learn if sine is like an even function or an odd function. So let's play around with that for a minute. Let's just goof around here. Let's do sine 10, get the answer. And then we'll do sine negative 10 and get the answer. Ooh, interesting. Sine 10 gave me 0.1736. Sine negative 10 gave me the exact opposite. So, is this an odd function or an even function? Some of you are missing this. This is valuable stuff. Sine of negative theta is producing the opposite of sine of theta. That's not even behavior, right? That's odd behavior. Odd behavior is when f of negative x produces the opposite of what f of x gives you. Okay, so we've just learned another rule that sine of negative theta is the same as the opposite of sine of theta. In other words, sine is an odd function. Now, we haven't graphed a sine wave before, at least I haven't done it with you. But does anybody remember what it means graphically for something to be an odd function?
Across the x and y-axis.
There's a certain sort of symmetry, right? What kind of symmetry is it? Maybe we can take a peek at the sine wave for the first time this year. Okay, this is called the sine wave. This is the graph of sine. Okay? What kind of symmetry does it have? Does it have y-axis symmetry? No. So it's not an even function. Does it have that unique origin symmetry that is required for an odd function? Yes, it does. If you view this thing completely upside down, it looks identical. Okay, so watch. I'll turn my projector. So if I turn my projector upside down, that's the same wave. A rotation by 180 makes it unchanged. My projector's very confused right now. But that shows me that it's an odd function. Give it a second. There we go. Okay, does everyone see that we just figured out that it's an odd function? We didn't prove it, but we believe it. You can do the same thing with cosine. We can come up with 3 rules for that. They are not all the same rules. Okay? Let's go on and try another one. Let's do cosine. Fill in the blank with an angle that works. Cosine of 47 equals cosine of what? And yes, 407 works again. Let's move around again. Cosine 47 and cos what? Raise your hand if you think you have an answer. Yeah, let's see. Harry hasn't answered yet.
Cosine of 4007.
4007. So you added, what did you add?
I just put another zero in the middle because I know if you got 360 enough times it comes up to 40,000.
Okay, so if 47 and 407 works, then you assume that 407 and 4007 works.
Yes.
Yeah, he's right. If you add enough 360s, you can get it to come out to 4007. Okay, yeah, what'd you put, Jack?
313.
313. Okay, interesting. What'd you put?
Cosine of negative 47.
Cosine of negative 47. Okay, so this one obeys slightly different rules. The first rule is the same. It's never going to change. The first rule is the same as the last time, that if you take theta and you add 360 to it as many times as you wish, that is not going to change the cosine value. It's the same exact location. Everything about the point is the same. It's just a different name. Okay, so this rule still holds for cosine. So I thought it was interesting that Jack gave me, what did you say, 307, 13? 313. Okay, so I'm definitely going to want a justification for that one. Can you explain why that's working?
Well, because it'd be on the other side, like, so it'd be flipped, like it would be.
So you're saying
on
if you
this
flip it
side
over
of
the...
x-axis, yeah.
Okay, so if you reflect over the x-axis, you're going to find another point down here, right? And the relationship between point A and point B in this picture is that they both have the same what coordinate? Yes, they both have the same x coordinate. It's true. And if they both have the same x coordinate, then they both have the same cosine value. See? So we're using symmetry to argue that point B works as well. How did you come up with 313 or whatever it was? 313.
360 minus 47.
Yes. So if this is 47, this angle is just going to be 360 minus 47. Right? Because this angle also is 47. So we have 47 above or 47 below. But if you're measuring the green, that's just a full circle except that red piece. So it's 360 minus theta gives you the same value as cos theta. So let's do that. Let's write that down. So cosine of theta and cosine of 360 minus theta are always the same. This makes me want to try like cosine of 1 degree and cosine of 359. You know? Let's try it. Where's my calculator? There it is. Okay, just for fun, clear the screen, cos 1, cos 359. Yep, 0.99987 or 47, yada yada. Okay, so I believe this rule is true as well. The symmetry argument is very convincing. Okay, this makes me want to ask what happens if I change my theta to a negative theta. For example, what about like cos 10 and cos negative 10? You know? What happens there? And Hava actually already tried cosine negative 47 on the calculator, and you got the same result as cos 47, right? Okay, so cosine of negative theta and cosine of theta are identical. Okay, you can test it out with any angle of your choice. You can use any input you wish. Okay, so let's try it. Let's do cos 10, cos negative 10. Sure enough, 0.9848. What do we call a function where f of x and f of negative x are identical? That's an even function. What kind of symmetry does it exhibit graphically? So cosine is an even function. This has y-axis symmetry. Let's just take a peek at a cosine wave or a day early on that. Let's just see if it's really symmetric to the y-axis. This thing's faster for graphing. So I'm going to do cosine x. Does it have the correct symmetry that every even function should have?
Yes.
Yep, right over the y-axis. We'll talk later about why it's a wave, but for now we need to predict it, and it seems true. You suppose there might be 3 rules for tangent? What do you think? Yep, there are 3 rules for tangent. So I don't have an assignment for you tonight. Figure out the 3 rules for tangent. Okay? Figure them out.